Hi, my name is Nils, and today I want to present our transfer interpretability method called TX-ray. This is work done with Vageesh, Kumar, Saxena, and Isabelle Augenstein. Our motivation for this is quite simply to watch neural networks learn knowledge. And the typical problems with supervised probing task evaluation is that they're only measuring expected knowledge semantics, and that they require manual annotation and thus cannot scale to uncover unforeseen semantics. So our goal here is to instead say, can we visually quantify and explore how language models learn knowledge during self-supervision, apply knowledge in a zero-shot fashion to a new domain data, or adapt knowledge via supervised labels. So the approach we choose for this is self-supervised interpretability, and specifically the principle of activation maximization, which visualizes what input features each neuron prefers, i.e. maximally activates them. So for the first research question, how language models learn, we took a random encoder and fed data to it, basically language model pre-training. What happens is the loss drops as expected, but we can also, for each token in the input, record which neuron it maximally activates. So basically for each neuron, which features it prefers. And we can do these activation recordings over multiple steps. And eventually both training loss and the model representations in the form of these token preference distributions will converge. And what we get is we get many activations for a feature in a neuron. We average them. And then we get these frequency distributions here. And in order to make them probability distributions, we simply normalize. So what we end up with is these activation behavior distributions from pre-training that visualize how knowledge was absorbed and can be interpreted. In the second research question, we want to look at how this pre-trained knowledge is applied to a new domain. So we feed a new corpus and we get different activations patterns on neuron preference patterns. And for each neuron, we can see if this activation preference is similar to the pre-trained corpus. And if it is, then the knowledge of the neuron from the pre-training transferred to the new corpus. And if they're different, there was little transfer for the neuron. We can also quantify and measure these differences. And in this case, because we have probability distributions, we use the Hellinger distance because it is a symmetric version of the Kolbeck library divergence. So what we can take away here is that we have out of domain generalization for neurons that have transferable knowledge or have the same activation patterns over pre-training and new corpus. And we also have over-specialized ones that have a large difference between these distributions. And in the end, TX-ray can be used to show the generalization to new domain data distributions per neuron. The last question we wanted to look at is, how does the supervised signal used to fine-tune the pre-trained encoder change the knowledge on a neural level? And what happens is, supervision specializes or refits certain neurons. It also adds knowledge, and this means some neurons during pre-training were not preferred. And now there are new neurons added that are preferred that weren't during pre-training. And also most of the neurons, over half of them, are now not preferred anymore after supervised fine-tuning, which means a lot of old knowledge was tuned down or even deactivated. Then we ran an experiment for this, a pruning experiment, where we use our method to guide pruning. So we pre-trained a language model in one domain, Wikitext2, fine-tuned it on another domain with labels and the IMDb binary review task. And here on the lower right, we can see for these neurons that we just discussed, for example, in A, if we prune half of the neurons that are now avoided or became unpreferred, we, for the end task, basically prune some noise and thereby increase generality. In experiment C, we can see that if we prune the most active preferred neurons, we lose generalization power. And indeed, we can see that if we prune the neurons that were specifically added during supervision, we lose a lot of performance on the test set and the training set. So this is very important knowledge, and it also tells us that this method can take apart unimportant, important neurons, added neurons, deactivated neurons, all that kind of thing. We also have some general takeaways, and our motivation here at the end and how we think TX-ray can be useful is that it can explore generalization and specialization at the individual neuron level. For example, for self-supervised pre-training, we kind of understand that a network builds general knowledge, and we can see that in here, in the red area down in the graph, that almost 90% of neurons are preferred and used, and that we have broad activations. In the zero-shot application of this pre-trained knowledge, we see that 88% of neurons are active, so it's almost the same, but we see that the overall activation mass here, this area, is a bit less. So we see a partial generalization to the new data. And then after supervision, we see two things. First of all, only 45% of neurons are still preserved, so over half became unpreferred and inactive. And we also see that the activation distribution here of the activation mass, or sum of activations, is highly peaked now, which means we can basically see supervision sparsifies and over-specializes pre-trained knowledge. Finally, we have some connections to older and newer than ours research. For example, for interpretability, there's activation maximization in vision and token attention tracking in transformers, if you want to apply it to transformer models. But one of the more interesting ones is a paper called movement pruning, which is the idea that during transfer learning, you should only prune the neurons that change the most, which is also what we did in this paper in the experiments we just showed you. However, we want to point out that pruning can be interpreted as force forgetting, and that it thus may only be useful in supervised learning. Thank you for your attention.